which is called parabola. Okay, so parabola, if we had it like this, it would be parabola would be like this, but because we have minus 2, we have to shift everything by 2. So instead of this picture, we'll have a picture starting at minus 2, negative 2. So it's going to be, for example, the next one will be negative 1, so only 1, and then here will be at 2. So it's something like this. Okay, does it look familiar? I hope my drawing is okay. So this is called parabola. Right? So again, the same idea. Now let's play with this a little bit. Suppose that I switch the variables. Suppose I write x is t squared minus 2t minus 1, okay, and y is equal to t minus 1. Suppose I write this. Same thing, but I switch x and y. I'm allowed to write any functions whatsoever. In fact, you're lucky I'm writing this. I could write some logarithms and exponential functions and what I'm going to do, right? So I can, right, but like I said, I start with simple examples. But here's a little twist. I just switch the order, switch the two variables. So now x is a complicated function, but y is a simple function. Now, we've learned the trick how to deal with this kind of parametric curves, and the trick was to express t in terms of x and then substitute. But in this particular case, that would be unwise, because the formula for t would be, if I try to express t in terms of x, would be very complicated. It would involve square roots, and so we don't want to do that, right? Instead, it's much wiser to use the second formula to eliminate t. So we write t is equal to y plus 1, and then we substitute in here. Okay, so then what I end up with, I don't have to calculate the second time, I just take the formula I had before, and I switch x and y. So what I end up with is x equals y squared minus 1. So see here, minus 2. Right? So see here, I had y equals x squared minus 2, and I said, this is great, this is the graph of the function x squared minus 2. So what I got now is not really a graph of a function in the usual sense, because usually we write the formula for a graph of a function by writing y equals f of x. It's not in this form, because I could try to express y in terms of x, but I would get like square roots and things like that, which I prefer not to have. But we should not insist on a curve being a graph of a function, because before we looked at graphs of functions because we were interested only in functions in one variable. So the only curves on the plane that we could possibly get this way, or curves like this, y equals f of x. But now we've grown. We look at general curves in the two-dimensional space, where actually the variables x and y become equal. We cannot say that x is more important than y, or conversely. So this should present no problem for us, because even if it's not a graph of a function, it's very clear what the curve is, because we got this curve just by changing x and y. So what does it mean? Geometrically exchanging x and y simply means a flip with respect to this diagonal, right? So if I flip, what do I get? I get exactly the same kind of thing, but it's now aligned like this. So it starts at negative 2, but now in x coordinate, and it will also have points like 1, negative 1, and negative 1, 1, right? And we just go like this. So this is precisely the mirror image of that curve with respect to that diagonal. And it's no more complicated than this. But this is a good illustration of the fact of how more general our curves are now than they were before. We don't insist anymore that they would look like this, but we also allow things like this. And you should be open to kind of playing with x and y as if they were completely independent, not trying to necessarily fit the same profile as y equals f of x, but for instance also allow x equals f of y. Okay, is that clear? So let's do a slightly more complicated example. How about this? Let's write x is a cosine of t, and y is a sine of t. Okay? So as I said, in principle, we can use any functions whatsoever. I could write some really ugly functions, and it will be a bona fide curve. Of course, in general, it's going to be very difficult to draw it, to plot it. You can plot some points. And next week, we will talk about other methods, which will give you a better idea, kind of qualitative ideas at least, about what the picture looks like. Because we will also talk about tangent lines, what tangent lines look like. So we have a bunch of tools, tricks and tools, which would allow us to get some understanding of what these curves look like in general. But in these simple examples, actually, we can somehow see the whole thing, right? And for instance, here, how do we see the whole thing? Well, the point is that these two functions, cosine and sine, satisfy a very simple equation, right? Which we know from trigonometry. We know this cosine squared plus sine squared is equal to 1, right? So we can use it to our advantage. So we can say that this is equivalent to this equation. And we already discussed the fact that this equation represents a circle, right? So in other words, we start with this parametric representation and we end up with this equation. So these are two equivalent forms of representing the circle. However, there is a small caveat. There is a small subtlety here, which is something which I haven't really kind of emphasized up to now, but now I'm forced to do it. Because remember, when I talked about the most general setup, remember when I wrote the formula for a general curve, I said the general curve is like parameterizing a curve by segment, and the segment had two ends, a and b, right? So when I wrote general formula, I'm switching s and y today. I also wrote this, where a and b are some numbers. So you have to remember this. Because if you are given this, in the discussion up to now, I was not paying attention because I never wrote any limits. And if you don't write any limits, by default, it means that it can take an arbitrary value. In other words, in the example of this parabola, I didn't write any limits, right? And so what I'm talking about is the entire parabola. The entire parabola is parameterized, if you will, by t going from minus infinity to plus infinity. If, however, you're doing homework, and in the homework it says t goes from negative 1 to 1, you don't draw the parabola. You only draw the part of the parabola which corresponds to the values of t between these two limits. And what is it? Well, for t equals negative 1, that's what? So that's, it's minus, okay. T equals negative 1. Let's do it. In fact, like we did before, right? So see, I don't have the answer right away. I have to count. So you have minus 1. So you have 1 plus 2 minus 1, right? So that's 2. And for y, it's negative 2, right? So x is 2, and y is negative 2, right? So it's this point. Now everything which is on this side is going to have t less than negative 1. So I erase it. Right? And likewise, next I look at t equal 1. So that would be what? 1 minus 2 minus 1. So that's negative 2, right? And if I put equal on here, 0. So it's this point. So if I'm told to look only at the parametric curve for this limits, it means that I only look at this part. This is what I have to draw. This is what I should look at. Okay? Now let's see how this plays out in the case of a circle. I was a little bit cavalier when I said that this formula is just represent a circle, right? The point is that, let's say if you start from t equals 0, for t equals 0, you get this point, right? And as you increase t, I hope you remember from trigonometry that x is going to decrease and y is going to increase. And for example, here you reach this point when t is pi over 2. You reach this point when t is pi. You reach this point when t is 3 pi over 2. And you come back here when t is equal to 2 pi. If you continue to increase your variable t, you will actually start making a second round, second circle, and so on. So you're actually going to wrap around the circle infinitely many times, right? So it's not correct to say that this is equivalent to this. What is correct is to say that if I impose the condition that t is between 0 and 2 pi, then this is really equivalent to the circle. Likewise, if I would, if you want, I can also say alpha plus 2 pi for any alpha. That would also correspond to this. But if, for example, I say, if I say that t, for example, from 0 to 4 pi, it's not just a circle, but our curve is not just a circle. Our curve is obtained by wrapping around the circle twice. If it's 4 pi, if it's 4 pi, if it's 6 pi 3 times, and so on, counterclockwise, right? So you have to be aware of this, that parametric curve actually gives you more flexibility, because parametric curve, for example, allows you to go through the same point twice, and even through the same curve twice, or 3 times, or infinitely many times. So you have to be careful when you start converting these parametric equations into this sort of more conventional equations relating x and y. You have to be careful to keep track of what the limits are. Any questions about this? Yes? In other words, what is the dimension of parabola and what is the dimension of a circle? Also 1. That's why we call them curves, right? So circle is one-dimensional and parabola is one-dimensional, right? And I know that it could sound a little bit anti-intuitive, right? Because you may think, one could think that one dimension is like a line, but as soon as it becomes curved, right, it's somehow more than a line, right? But see, the point here is not that we have to, let me backtrack. The point is to separate two things, to separate our geometric object from the ambient space where it lives. A circle lives in the plane, right? It is embedded into the plane. But the plane is not a circle. The plane is the ambient space. It's like its home. It lives there, but it doesn't mean that the circle is two-dimensional. Dimensionality is a measure not of the dimension of the ambient space. It's a measure of how many independent variables you have within your object. In this particular case, we were able to parameterize the entire circle, but by one variable, namely variable t. For each value of t from 0 to 2 pi, we got one and only one point on the circle. Well, more precisely, for 0 to pi, we get the same point, but that's not what it is, right? So in other words, we have been able to identify the circle with an interval from 0 to 2 pi. And that's what parametrization is all about. It's about mapping or establishing a correspondence, or more proper mathematical term would be one-to-one correspondence between your curve and an interval. Now, the interval clearly is one-dimensional. And when we make this procedure, we identify this interval with the circle. Each point here goes to one and only one point here. So that's the reason why we say that this is also one-dimensional. And more concretely, this is what is expressed by this formula, because we say that both x and y coordinates are expressed in terms of t, right? That's why it's one-dimensional. Put a different way, these are not all possible values of x and y, but only values of x and y which satisfy this equation. In other words, there are two independent variables x and y, but there is one constraint. So the rule is the number of independent variables minus the number of equations. That works almost always works, but it's a good rule. So in all situations, we'll consider it will work. You see what I mean? Yeah? Any other? Yeah? Direction of the graph. So the question is, I have to repeat it for the worldwide audience. The question is about the direction of the graph. This is a very good point. So in fact, here, as t increases from 0 to 2 pi, this is traversing the circle counterclockwise, right? If, for example, I made a change, if I wrote like negative t, for example, right, it would go clockwise. So in principle, if we want to be really pedantic, and I guess we should be, I mean, why not, right? We should be. We have to specify also in which direction does this parameter reverse the curve. For example, in this case, it would be this way, with negative sign, it would be this way. Likewise, here, it was this way, right? Because negative 1 corresponded to this point, and 1 corresponded to this point, so clearly we were moving this way. So the answer is yes, you should keep track of this as well. Anything else? Okay, so now let's do one more, and I think time is up. Oh, because let's look at this parameterization, okay? If t is positive, negative t is negative, and the negative angle will correspond to this, moving like this, right? This is minus pi over 2, negative pi over 2, or so on. Now, I know that the lecture is almost over, okay? And everybody wants to get out of here, right? Now, I will not keep you more than you have to be here. I promise. Right? It's 5 o'clock. It's over. You know, even in mid-sentence. But if we start thinking about leaving now, 5 minutes before, it's not going to help because people start doing stuff and moving, and so then it means that the lecture is not 50 minutes, but it's 45 minutes. Okay. So then I might as well finish it 5 minutes before. But then of course you'll start even 5 minutes before, and so on. So that's, by the way, this is a mathematical argument. Now, so to avoid this, I would like to ask you not to move. Well, not to make any unusual movements, which you will normally do. In other words, act in the same way between the beginning of the lecture and the end of the lecture. Only when it's finished, then you kiss. Okay, just a simple request. Because we are many people, and this will help everybody. All right, so we have one more example, and then I'll let you go. Maybe let me just do a small variation on this. I already did one, so I put negative sign. Here's another variation. How about I put 1/2 here? If I put 1/2 here, this will not be true anymore, because if I take x squared, I will get 1/4 of cosine squared. Right? But there's a very simple way to compensate for this. Let's take 4x squared. If I take 4x squared, it's going to be 4 times 1 over 4. So that's again cosine squared, and everybody's happy. So that means the equation becomes 4x squared plus y squared equals 1. And what does it represent? Well, what we have to do is we have to just stretch everything along the x direction by a factor of 2. Because, well, 2 is because of this 1/2. That's right, sorry, I meant shrinking everything by a factor of 2 because of this 1/2. So what it's going to look like is that it will now cross the x line at the points 1/2 and negative 1/2. But the y line, y-axis, it will still cross at negative 1 and 1. And so it will look like this. And that's something which is called an ellipse. So you see, this is not the circle, but it's very similar to a circle, and we use our intuition, our gained knowledge about the circle, namely that we knew what this was, to represent this curve, because we see that geometrically this is going to be like a circle, but it's just squished by, or shrunk by a factor of 2. Okay, good. So now, just in the remaining 2 minutes, I will begin, and I will let you finish it on your own. Sometimes you're going to be asked to write the parametric representation for a curve which is described in a different way, in words, for example. In other words, some people will tell you, or in the book when you do the homework assignment, you will see a description of a curve, and you will have to represent that curve in a parametric form. And here is a very typical example, which is called cycloid. So this is a curve which you obtain in the following way. You take a circle of radius 1, so this is 1, right? Okay, or think of a disk if you like, and you put it here. It's like a wheel. Think of it as a wheel. And then you have a marked point. There's one point here, which is now at the bottom, which is now exactly at the origin of this coordinate system. And then rotate it to the right. Roll it to the right. Think of it as a wheel, and just roll it to the right. And let's see what happens with this point. Look at the trajectory of this point. So this is actually a very nice example, because I was telling you that one of the ways to think about parametric curves is to think that there is a point particle which is moving, and as it moves, it sweeps the trajectory, and that's your parametric curve, right? And so what will happen is that it will go something like this. Oh, sorry, that's not this. It will go. That's to reach. At some point, it will reach the highest level, and then it will come back, and then it will do the same thing. Repeat the same trajectory many times. Right? So qualitatively, it will look like this. But now you have to write a formula, or more precisely, 2 formulas. You have to write x as a function of t, and y as a function of t. Right? So that's what you need to do. And so this is actually an example. It's a good example. It is in the book. And I will just give you a hint. The first hint is to decide what is a good auxiliary parameter. So when the circle moves, let's say it moves this way, so then the point could be somewhere here. It becomes somewhere here, right? And so the question is, which parameter are you going to use? And so in this particular case, the good parameter is the angle of rotation. By how much has the wheel turned? And then after this, it's a simple trigonometry to find the coordinates x and y of this point as a function of that coordinate. So there are 2 parts, right? You first find the good coordinate, which in this case is angle, and second you use some methods like trigonometry to express the x and y as functions of this coordinate. That's how you do it. Okay, that's all for today, and we'll continue next time.